Osmosis. Why drinking salt water causes dehydration? I think most people know that if you're stranded in the ocean, that you should not drink salt water, right? Because as thirsty as you are, drinking salt water will actually make you more thirsty. It will actually take water out of your body rather than putting it in. And that is because of osmosis. Osmosis is the flow of a solvent from a less concentrated solution to a more concentrated solution. And so we observe osmosis when solutions containing high concentrations of solute draw solvent from the solutions containing a lower concentration. This just doesn't mean a lot. Okay, why? Here's a picture. I think I've got the picture figured out now. So here's your intestine, and this is inside your intestine, and this is an example of what happens if you're drinking salty water. So here we've got salt in this water that's in your intestine. The walls of your intestines contain semipermeable membranes, which allow water molecules to pass back and forth. They don't allow larger things to pass back and forth. So here on the other side of the intestinal wall, your body is mostly aqueous solutions. Oops. So there's an aqueous solution here. It has some salt in it, but at a lower concentration. And so what's going to happen is this salt water, which we say is a thirsty solution, is going to pull water through your intestinal membranes into your intestines and out. We all know where that goes. So it's actually pulling water out. You drink salt water, you're actually dehydrating yourself. You're not hydrating. So that's not good. Here's another picture. This is, we've always called these U-tubes, and now that sounds funny, doesn't it? Because that's not U-tube. It's a U-shaped tube, okay? It's got two arms, and in the middle here is a semi-permeable membrane. On this side is pure water. On this side is a salt solution. And initially, the levels of liquid in both sides are the same. You leave that alone for a while, and the solution level on the salty side goes up, and the solution on the water side goes down. Is that a normal thing that happens? You just see the level of one side of something going up and the other side going down? That's not normal, is it? What's happening is osmosis. The water is going over to the concentrated solution. We're not going into a lot of detail about this. So the way I think of it is, nature likes to level things out, right? You see a stream and it's flowing down until it gets to the lake or whatever it's going into. It's flowing down. You don't see water flowing uphill. You don't see charges separating. You see them coming together. It's trying to level and equalize things out. So that's kind of my chemistry land picture of this. Is that this is very not concentrated and this is concentrated. And by the water moving over here, it can lower the concentration. It's diluting this side. And it wants to move over here until the concentrations become equal. Well, sometimes that's possible. Here it's not because there's no salt over here. So the water's going to keep going this way, but as it does, the water level in this arm rises, and now it's going against gravity and against atmospheric pressure. Both of these arms are open to the atmosphere. We saw tubes like this when we talked about pressure, and there was mercury in it, and we said that the difference in the heights of mercury on each side of the arm related to a difference in pressure. Here the pressure is the same, but there is a difference in these levels. That difference is called the osmotic pressure. It is a pressure, but it's a pressure that the water is forcing by trying to come over here. And this osmotic pressure will depend on the concentration, the relative concentrations of the solutions. Osmotic pressure is a colligative property. It depends on the concentration of the solute particles, not on what they are. It could be sodium chloride, it could be sugar, it could be potassium dichromate. It doesn't matter. If the concentration is the same, you're going to have the same osmotic pressure. More concentrated solution, greater osmotic pressure. The membranes of all living cells act as semipermeable membranes. So if you put a living cell in seawater, it's going to lose water through osmosis and become dehydrated. Freshwater fish do not like to be placed in the ocean. It sucks the water out of them. But sea fish, ocean fish, losing my word, I don't know, what do we call those? Oh, fish that live in the sea. Saltwater fish, thank you. A saltwater fish doesn't like to be put into fresh water because it absorbs too much water. That's not how their cells are set up. So we can look at this in terms of blood cells. So blood cells have membranes, and they are semipermeable, and they are sensitive to the relative concentrations of solutes on the inside of the cell and on the outside. And so there are three different situations, and we're going to look at the prefixes here. Iso is something that means the same, a prefix meaning the same. So an isotonic solution has a solute concentration in the surrounding fluid that's equal to what's inside the cell. And so when we have normal red blood cells in an isotonic solution, they retain their normal shape. This is what they're supposed to look like. A hypotonic solution has lower concentration. Hypo means below. So this is a lower concentration. When we have a lower concentration outside than inside, the water flows into the cells and causes them to swell, and if it continues, they will actually burst. Bursting red blood cells in your veins is not a good thing, right? And the other extreme is the hypertonic. Hyper meaning more, hyperactive, more active. Hyper, the surrounding fluid is more concentrated. More concentrated draws water out of the cells and causes them to shrivel up. And that's not a good situation either. And there are implications of this for cooking. We have time, so I'll tell you a story. When my husband and I were first married, we were both in graduate school, and so we didn't have a lot of money. And one of our favorite dinners was teriyaki hot dogs. My husband is Japanese, and his Japanese grandmother, was very fond of hot dogs. She even put them in sukiyaki and all kinds of very authentic Japanese dishes, and she loved to use hot dogs in them. But teriyaki hot dogs are actually really good. You take a hot dog and you score the skin of it, and then you boil it in teriyaki sauce. And we just make our own teriyaki sauce, so it's really cheap. So I made teriyaki sauce, and I made teriyaki hot dogs, and I made a pot of white rice. And of course, he was late for dinner because he was working on his research, and I was fine with that. So I went ahead and ate dinner, and I left the hot dogs in the teriyaki sauce to keep warm. Well, by the time he got home, and I went to pull those hot dogs out, they were hard as rocks. Not because they were overcooked, but what's in teriyaki sauce? Sugar and a lot of salt. Okay? So here's I'm going to give you my secret recipe for teriyaki sauce. Equal parts of sugar and beer and soy sauce. And if you want to, you can throw in, ginger and onion powder and stuff like that. Lots of sugar, lots of salt. It was a hypertonic solution. Hot dogs are salty, right? But not as salty as teriyaki sauce. It pulled lots and lots of water out of those hot dogs, and they were just like little rocks in there. So I never did that again. So, end of story, end of chapter. Now, don't leave just yet, because I have a video I have to show you.